Good morning, everyone. So today we will talk about limit cycles. So this is gonna be a session. This is six already, and I will cover two sessions because the topic, so the content is pretty long. Well, what are limit cycles? Limit cycles are like enclosed trajectories that we can find in the first portrait, and they are isolated trajectories. These limit cycles are actually not fixed points. They are not fixed points. They are just like another mathematical feature of nonlinear systems. So, as I just said, is a mathematical feature of nonlinear systems. So you cannot find limit cycles in linear systems. So some of you may wonder like, but we can have still oscillations in linear systems. And yes, we already saw that two-dimensional systems, even if they are linear, they can have the so-called fixed point centers. And therefore they have oscillations that are actually steady. But they are non-isolated oscillations. And in this case we have isolated oscillations. This is different. And these are not fixed points. Now, therefore, it's not simple somehow to state or to discover limit cycles in nonlinear systems. Sometimes we will talk about like certain techniques to like define and say, yeah, these systems in this region of the phase plane exhibits a limit cycle. But this is not straightforward. Okay, and you may wonder, why do we want to study limit cycles? So limit cycles is a very important phenomenon because it describes self-sustained oscillations. So if you think this in terms of energy, there is like a given point, a source of energy that fits this somehow oscillation and it grows in amplitude, and at some point the damping effects somehow balance the growth of the oscillation, and then you end up having a self-sustained oscillation. So in my field is thermoacoustic instability is what I do, and that can actually be explained as these acoustic oscillations that combustion chambers exhibit when they have the so-called combustion instability. So you may have a moment in which you change the power of your engine, so you just add a little bit of mass fuel, and then suddenly you can have strong vibrations. So, what linear theory predicts is you have a growth, a perturbation that will grow. This is something we already saw. Now, what nonlinear systems allow is to be able to predict until when this amplitude will grow, until when this perturbation will grow, and being established afterwards as a limit cycle. So you can think about limit cycles as a stable limit cycle, as an unstable limit cycle, and then as a half stable limit cycle. All of them are super interesting. So the first one is somehow the one that might be very common, or let's say to explain self-excited oscillations. You can have, imagine you have, this is time and the amplitude of the oscillation, and then you can have a little perturbation, and then you will have the oscillation start growing, and you may say that it follows an exponential growth, but it keeps growing, and then is this exponential growth, which is valid just at the beginning, then becomes just like an envelope that developed into a limit cycle. So the amplitude of the limit cycle. Okay, this is a little bit. Okay, I just draw again the limit cycle just because it was not on the envelope, just not to avoid confusions. So you see this like in the phase plane, you can think about like an spiral that just start growing until reaching little by little this closed trajectory, which is the limit cycle. In addition, we have the unstable limit cycle, which is actually somehow opposite. You may have a given oscillation that can be easily destabilized. So imagine you have again the envelope in here, so you have the oscillation, and then any perturbation will make that this oscillation somehow disappears and then goes to the origin and then just die. Or the other possibility is that the oscillation actually grows until maybe reaching another stable limit cycle. So this either going to the origin like this, doing some spirals, or just going away, depends on the direction of the perturbation. Okay, and we have this one here that is also super interesting. Actually, is like thinking in terms of where the perturbation is coming from. If the perturbation is actually from the outside, so you just make this limit cycle grow in a moment, so the amplitude grow, then it will go back also in spirals until arriving to the actual limit cycle you had at the beginning. But if you do a perturbation towards in here, so it means that you just make the amplitude decrease a bit at a given instant of time, this perturbation is actually unstable, and then you will go away from the limit cycle until reaching the next fixed point, which is going to be in this case an attractor. Note that you can have the other or the opposite situation when you have here a repeller, and therefore any perturbation will grow until reaching this limit cycle, but any perturbation in this direction will make the oscillation keep growing. Okay, so if you have the opposite situation like this, I just draw, so you have like a repeller, then it develops into the limit cycle, and then you have another perturbation maybe that goes and make this oscillation keep growing. So you can represent this like this situation. Imagine you are actually, this is actually that happens in combustion chambers, or let's say in a more general way in vibrations, let's call it pressure. Then you have the initial exponential growth, then you just establish a limit cycle, so you will have something like this. And for some reason you may think, okay, the limit cycle is reached, it's gonna remain like this, but suddenly you can have like a second perturbation and develops into another limit cycle. So there is like a switch in the oscillations presented by the system, and this can actually occur because you have half stable limit cycles. Okay, just so maybe be a little bit more precise, in order this to happen, you need another trajectory here associated to a stable limit cycle, so that you have this other envelope. Let me just introduce you to a very classical oscillator, which is called the Van der Pol oscillator. This is a very simple oscillator that exhibits a self-excited limit cycle. So you can think, so just let's look at this one, okay? And if you remember, this classical or this equation has the shape of an oscillator. Let me just write it down. So the oscillator would be like x dot plus mu x dot plus x equals 0. So this is a classical linear oscillator. When you have, if you think about the spring damping system, you have here the stiffness. So let's say this K in here, and you have also the damping term, which is mu. So when mu is positive, you have, again, you have damping. But if for some reason you change here this sign, if you have a negative damping, it means that you have actually a source. So you are creating or you are introducing energy to the system to make it grow in amplitude. So that could be described with this simple linear oscillator. Now this idea of switching the sign of this mu can be actually achieved by introducing this kind of nonlinearity in the damping. Okay, so basically when your oscillations are very small, or let's say less than 1, this term is gonna be negative, and therefore you will have a source of energy in your system that make it grow in amplitude, so the oscillations. However, when you arrive to this threshold of 1, and then you are a little bit larger than 1, then this term becomes positive, and therefore the damping term will be actually a damping term because you have a positive sign. So you will damp any oscillation that comes. So around 1 you have two contracting systems, something that make the system grow in amplitude for values slightly little than 1 or for smaller values than 1, and a mechanism that make your oscillations damped if you have your oscillations being a little bit larger than 1 because of this. Okay, then you will find always a limit cycle when you have this balance between gain and damping, source and sinks, let's say. Okay, but when I'm talking about source, I'm not talking about a source in the right hand side of the question. Maybe pay attention. I'm just trying to say that you introduce like an external source of energy by means of this term. Okay, well, and this is how it looks like. So depending on the value of mu, you may have a situation where you have the oscillation start growing, and then just in this case just make a little, not even a one turn, and you reach this limit cycle. And again, you can actually see that this limit cycle, as it shows in here, is not a harmonic oscillation. It means that it contains more than one frequency. So if you do the Fourier transform of this signal, you will have several peaks. Again, when you have a system that exhibits this limit cycle, the first you could do is to see the fundamentals. How can you model this system with very small amount of dimensions? If you are able to describe a system as a van der Pol oscillator, that's actually a big gain, because it means that you are able to describe this complex system by just this little oscillator that has been studied a lot, and then you can actually understand more the system of interest that you are investigating. So as I told you, it's interesting to know if you have a system of equations, if you're able to derive the equations that describe your system, to see if that system actually exhibits limit cycles in its somehow mathematical structure. So this is actually different from fixed points, because for fixed points you can actually, as you just saw, you have this fx of y equals 0, gx of y equal to 0. You find the fixed points, then you just establish the stability just by doing the analysis of the corresponding Jacobians and so on. For limit cycles, it's not simple because it's not just a fixed point. Then you just have to carry out like a more involved analysis. But there are some strategies to do that. So the first thing is to see that if you have a system where the energy always decays in time, there is no way that you will have a closed orbit, because there is no this somehow counteracts effects between gain and damping, the thing we were just discussing before. If it always damps, or if your energy always goes away from the system, it means that the system will eventually reach a equilibrium point that is stable. which means maybe just an attractor and no oscillations at all. There is an interesting way of finding out whether we have or not a limit cycle. This is by carrying out the Poincaré-Bendixson theorem. So it's like to ensure a trapping region in the phase plane. So this is something we will just do in an example, but before, let me tell you the basics. So imagine you have the phase plane, and you find a region when you have, for example, this situation. You have in this case a repeller. Then you can see the evolution of your trajectories going towards the limit cycle. And in the same way, you have a given initial condition that evolves like in spirals until the limit cycle. So you can think this or deconstruct it in this way. When you just see, you assume you know nothing, but you just evaluate the flow on the boundaries of this contour that you just created. In here, just making a hole in here and just grabbing a region close to the limit cycle. And when you just point, you just like get some points in the phase plane and portray the direction of the evolution of the trajectories. It means the arrows. You will see that anything that is outside will actually evolve and will go inside. Everything that is inside will go inside this region as well. So everything will evolve in this case. So it means that you will have like a positive flow coming from both boundaries, and therefore you can assure you have actually a limit cycle. So this is the understanding of the main idea of this Poincaré-Bendixson theorem. Okay, so we have two equations, two-dimensional system, and these are nonlinear equations. So this function describes the evolution of x, this one the evolution of y. And what is the purpose of the exercise? The purpose of the exercise is to just develop the phase portrait. So just get the points and get some arrows inside a given region, and then being able to establish if this Poincaré-Bendixson theorem applies or not. If it applies, it means that this system, as we see in here, exhibits a limit cycle. Okay, so the first thing is to draw. So we could eventually get every fixed point in the phase plane. So we have the phase plane, and just point every single, or just we choose some points and draw the corresponding arrows, which is actually the direction is defined by these equations. Okay, but that would be maybe super expensive. We can do this in a much more systematic way, in a much more simple way. And the first thing we have to do is to introduce the concept of null clines. Null clines means that, a fixed point is when you have x dot and y dot, or both of them being 0. Okay, but a null cline is just when either x dot is equal to 0 or when y dot is equal to 0. Okay, so we will do that, and while doing, we start somehow understanding and learning. So let's assume first that x dot is equal to 0. So this equation will become this, and the other case is when y dot is equal to 0, we will have this equation being 0. Then you just reorganize and have these two equations. So the first thing, let's draw this. Okay, the first thing we have to do is to just draw these two functions. And now let's put some colors to this. So we will just describe this function with a blue color, and the other one with a red color. So let's start with the first one. We have that y of 0 is equal to what? 0. We also can say that the limit when x goes to infinity of y is equal to what? Yeah, 0. So you can see that when x goes to infinity, this term actually is basically given by x to the square, so a just becomes negligible, and therefore the denominator is larger than the denominator, and therefore we have this case. Okay, it is also of interest, you will see, just to be able to plot this function to know if it has maximum or minimum. Therefore we just need to derive this equation. Okay, so we need to have dy, let me put in here dy, okay, just to save time I just did this derivation, let's say offline. So basically just dy dx of this function, the blue function, and the idea is to find the equate this to 0 and find the maximum. So we find that if we're interested in the positive range of x, we have just one point in here that is going to be equal to 0. So it means we have one maximum, and it's found at x equal, let's put it in here, let's put it raise of a. So based on what we learned, we know that the maximum is somewhere in here, and we have y 0 when x equal to 0, and y is equal to, or goes to 0 when x goes to infinity. Okay, now let's carry the same analysis to the second function, which is going to be done in red. So y of x, y of 0 is equal to, yeah, b over a, and again limit of y when x goes to infinity is equal to what? Yeah, 0. And also we find the maximum or the minimum, so we have to derive this equation. So based on this, I just realized that we don't have any maximum, only actually at x equal to 0, as you see here. So you can just put pause and look at the expressions. So the first thing is that we will consider this point to be b over a. Maybe I don't know if I already mentioned, but I think it's important to mention it. B and A are both positive numbers. This is the definition. Okay, we will then find there are two things missing. First, we have to know which of the blue or the red system goes to 0 when x goes to infinity in a faster way. And we can already realize that this is going to be the one that goes faster, because it decays, or the decays as a rate of 1 over x to the square, while this one, taking into account this nominator, will decay in a rate of 1 over x. So this one goes faster to 0. Okay, so we already know that we will have at least something in here like this. And we know that we will start from here. Now we need to find out the crossing point, this point, and I'm asking right now, which is actually this cross point. When x dot and y dot are the same, it means that both x dot and y dot are 0, which means that we have actually a fixed point. So this is going to be the fixed point when the two nucleons cross. So we have x over x squared plus a is equal to b x squared plus a, which basically means that x is equal to b. So this is going to be point b. Okay, we can now then draw the whole function. Okay, and we have the two nucleons drawn. Okay, so now what is actually necessary is to draw the vectors along these two nucleons. So if we want to draw first the arrows along this nucleon, we know that x dot is equal to 0, so there is no allowed change in x, which means that if we have an arrow, it has to be vertical. So since we don't know yet the direction, I will just draw these vertical lines along this blue trajectory. Okay, and if we just look at the other equation, we have a similar situation, but the changes are not allowed in the y direction. So we will have vertical trajectories, horizontal trajectories along this line, just to represent that we have an arrow with a direction either to the right or to the left. So this is horizontal. Okay, just forgive me if it has a little slope. Okay, now the idea is to see what happens above and below the nucleons. So the direction of x, the direction of in y, so the rate of change. So we need inequalities, and so we can start doing this. So we can actually ask the question, we want that x dot is larger than 0. So it means that minus x plus ay plus x squared y is larger than 0. Okay, then we just need to solve this inequality, which is basically just minus x plus y a plus x squared larger than 0, then y is larger than x over x squared plus a. So we can right now say that above this blue curve you have an arrow pointing in the right direction, because the growth, so the change of rate of x, is positive. So just to denote this, we will just put maybe with a white marker just little flows to the right, because we know that this is flowing to the right. So conversely, we can say that below we have the flow going to the left. Okay. Okay, now we can do the same thing for the second equation. We ask ourselves the same question. So if we have the y dot larger than 0, we want then to have b minus a y minus x squared y larger than 0, and we just solve this inequality. Then we have y x squared plus a larger than 0, and then we have y is smaller than b over x squared plus a. Okay, so now we can know what happens with y. So the rate of change in y. So above this red curve, we will have a negative change, and below we will have a positive change. Okay, so we will just put the arrows like this, and this is going negative. Okay, so okay, now that we have the directions of the arrows in the x and y direction, then we can just actually draw the actual arrow. So just take note that the actual slope of the arrow is not exact, because we don't know yet how, if the x arrow, for example, is much larger than the y one, or the other way around. This is just an indication of the direction. Okay, it's not just that I know exactly the slope. Okay, we continue doing this. Now that we have drawn the arrows, I will just erase the components just to make things more clear. Okay, so now we have the arrows we just pointed. Remember that I don't know the slope, it's just an indication, but we can see already something interesting, that is like a sort of rotation around this fixed point. Can you see this? Now, because we know the direction of the arrows, we already know also the direction of these vertical and horizontal lines. So let me just draw these arrows just to make things more complete. So after doing that, we see like with more clarity this vector field that is coming like evident in this phase plane. Again, something to remark in here is, if you see the direction of the arrows of the along the null lines, you will see that the direction changes after the fixed point here, also here. So this is a characteristic of this intersection of the null lines that we will also repeat in other examples afterwards. So since we want to prove that this vector field has a limit cycle, so we want to prove it has or it does not, we will see. We will make use of the Poincaré-Bendixson theorem, which means that we need to first define a region. So let's like a region in here, so that we are sure that on the border of this region we defined, all arrows are pointing inwards. Since we are around this xy axis, so a natural choice is to define the region or the borders below this region to be this xy. Then we will just see how we define the upper boundaries of the region. So we start with the x-axis. Then we just take the equations again, and we'll see at x equal to 0, at the y equal to 0, we have x dot equal to minus x, and we have y dot equal to b. So from this we know then that the arrows are actually pointing inwards along this x-axis, and a little bit shifted like to the left, something like this. Okay, and now we do the same thing on the y-axis. So when x is equal to 0, we have x dot is equal to ay and y dot is equal to b minus ay. Here we don't know still the direction of y. We still need to do maybe some inequality to solve it. So y dot in this case is larger than 0 when b minus ay is larger than 0, which means that y is smaller than b over a. So now we know that the vectors is going to point in the x direction and it's going to be going also in the upper direction below b over a. So we have something like this. So you will see that at b over a the slope is actually 0 and then it changes direction. Okay, now we have to define the upper region of this box. So a natural choice that we may think is, imagine you just have a line. Let's go for example in this direction like this and like this. But and in that sense we will have like arrows going in here inside, because we already know that they go to the right and they go in the negative direction in y, so the rate of change in y is negative. However, if we define this box as in this case, we will have something like trouble in here, because well we will have actually the arrows will also go in this direction, and then we don't somehow design a correct trapping region. So maybe we have to rethink things and design something slightly different. So maybe the idea is to somehow design like a triangle. So instead of this square we will have already said maybe sort of triangle makes the job. So the idea now is to, if we want to get this triangle, we need to know the slope of the corresponding like hypotenuse. So that before doing that, we have to somehow get a way of computing the slope of the arrows. So here, remember we have this slope like this. And this is given by y dot and this is given by x dot. So we can actually, we need this operation, we need y dot over x dot to know the slope of this arrow, and this is just simply given by the expressions again. So we have minus x plus ay plus x squared y over b minus ay minus x squared y. Okay, I have factorized the expressions. Well, now we are in here, so what can we do? Maybe we can actually also define like a threshold and say what is the condition that we have to have so that the slope is larger or smaller than minus 1. So the question is actually this: y dot x dot is larger than minus 1. For which cases? Okay, now we have just to solve this minus x plus y squared okay, larger than, then minus b plus yx squared plus a. And you just see here that they have these two quantities that just go away, and then we have that minus x is larger than minus b. Well, in other words, that x is smaller than b. Okay, so b is here, let's remember. So this is the distance b. Okay, let's draw now a slope equal to minus 1, like this. Let's assume this is minus 1. And the first question that we have is, what does it mean to have a slope that is larger than minus 1? It means a slope that it gets closer to 0. So that means that we will have a slope that is getting closer to 0, like this. And when we have x larger than b, we have the opposite situation. So we have a slope that is smaller than minus 1, which means a slope that goes towards minus infinity. So in that sense, we will have something like this. Okay, so what does it mean now? That we can actually have a trapping region if we define a triangle like this with a slope of minus 1. But it's going to be a trapping region only when x is larger than b, because you will see that you will have these arrows coming inside. In here it doesn't work, but it's easily solved because we can just define between x0 and x equal to b just slope equal to 0. So let me just draw the final domain we are aiming at. So under this dotted line, we can just see that we will have arrows coming inside in here, and also the arrows will come in here like this. So we already see that there are some little mistakes in the first assumption of the direction of the arrows. We can, for example, delete this one. Delete this one because it was not well done, and then just put the corresponding trapping region. Okay, so this is what a slope. Okay, so we're almost there. We have defined so far this. Now we need something in here, but that's pretty simple because we just see that for below blue everything points to the left, so we just need a trapping region like this vertical, and that's all. So we have already defined our trapping region like this when we see that all arrows are pointing inside. So based on this, we already know that there are two possibilities. First of all, we know that there is a rotation around the fixed point, okay? And this rotation is not caused by a center or something like this. It's caused because there is the possibility of a limit cycle. Now, there is also the possibility that all this oscillatory behavior of these arrows, they decay little by little until approaching an attractor. Okay, so in that scenario, we wouldn't have any limit cycle. We will just have oscillatory trajectories approaching a steady state situation. So that is defined just by evaluating the stability of the fixed point. So if we are able to define that the fixed point is an attractor, we already have no limit cycles at all. If we somehow find out that this fixed point is a repeller, then we will have automatically a limit cycle, because you would prove that if you just put a little region around this fixed point and it's a repeller, then all arrows will actually point outward. So inside this region we have defined. So okay, let's go to this to the next slide. So this is a figure also found in the book of Strogatz. We have here the trapping region we have designed, and a situation or an eventual situation when this fixed point is a repeller. So you can see that eventually you will have a limit cycle evolving inside this region. Well, maybe just a note by passing, this Poincaré-Bendixson theorem actually applies only in two-dimensional systems. In three-dimensional systems, we have the existence of chaos. Therefore, there might be the possibility in that scenario of 3 dimensions that you still have an oscillatory behavior inside, but you never reach a limit cycle. It just oscillates forever, confined in the region you just designed. But this is only happening maybe in situations of 3 dimensions. 2 dimensions, the only possibility when you look at this is that you will have a limit cycle. Okay, so we could proceed and find out the stability of this fixed point. So you know how to do it already. We just have to find the Jacobian around this fixed point and then find the conditions of whether having a repeller or an attractor. And this condition is going to be actually given by the ratio of B and A, these coefficients that are positive defined in the example. Okay, so we will not do that, and we will see the results. So this is what is found. So if you have this region, you will see that you have actually an attractor, and therefore there is no limit cycle. In this one, you will have a repeller, therefore what happens in the region is gonna lead to a limit cycle. And this is the situation of this. So when you have this being a repeller, so you will see that any oscillation, any initial condition in this region will go towards the limit cycle. And also, if you are inside, any initial condition inside this region will also lead you to the limit cycle. So when we were talking about fixed points that were complex, we had the situation of spirals. So a spiral could grow, so if it's an unstable spiral, or could decay towards zero if it's an unstable spiral, or could be just oscillating forever at the same amplitude, which is the situation of a center. Now, all these three cases, spirals, stable, and center, they oscillate at the same frequency. Okay, when you just find out the complex plane, you will see that the real part is the growth rate, and the imaginary part is related to the frequency of the oscillation. So this is something that will happen very close to the fixed point. When you go away from there and we are talking just, instead of fixed points, we are talking about limit cycles, these signals, so the oscillations, they are not as simple as the cases of spirals and centers, because they could change in terms of frequency content, so they can have many frequencies, and the amplitude can also change depending on certain conditions, okay, depending actually of the structure of the problem. Then the idea now is to see how can we start analyzing these limit cycles. So now we will just face the problem of the so-called relaxation oscillations. So when you can have actually two time scales inside a signal. And to start this analysis with the van der Pol equation is a very good idea, because we have an example where we can have two different time scales. So a part in the oscillation that goes very slowly and one that goes very fast. And this is actually given by situations where you have a very large value of mu. So the idea we will analyze now is the van der Pol equation that we just introduced some slides before when mu is very large, so much larger than 1. The first thing we have to do is to go into the language we know to talk, is two first order differential equations. So we will just change this by this equation, and this is just some mathematical procedure, and when f is equal to this. So these two equations are equivalent to the, or are the same as the van der Pol equation. Okay, so when you look at this equation, you may already realize that we can treat this as with this concept of null clines that we already saw in the previous example. And when our null cline would be given by y equal to fx. So when y is equal to fx, it means that x dot is equal to 0. Okay, so let's plot this null cline. Okay, so we will have x and y, and let's plot this. So a very simple way of plotting this is just to know, for example, that when fx, f of 0 is 0, so we already know that we have here, this is a point of the function, and we can derive this as well. So the x is equal to x to the square minus 1, which means that the slope at 0 is negative. So we already know something like this. We have something like crossing in this sense. Since this equation is actually a third order polynomial, we know that it has 3 roots. So this is the first one we already plotted, and we have 2 other ones, let's say here. So based on that, let's say the only possibility is that we have one maximum in here and one minimum in here. So we just draw it. Okay, so we have drawn the null line. So if fx dot is equal to 0, it means that we will have vertical trajectories. Let me just plot it with blue, like this. Right now we don't know the direction, but the direction is easily given, so we just have to see the second equation here. So for positive x, we have a negative y. So we have pointing in this direction, and this one in the pointing the upward direction. Okay, now let's start the exercise pointing just any point in the phase plane and see where we think this arrow goes to. So the arrow indicating the direction. So let's put a point in here. So if we look at the equations, we can see what? First of all, that the change in x has to be positive, okay, because in here we have y larger than f of x. We are above the curve. Okay, this is the first indication. And the second indication is that remember that mu in the example is very large. Okay, So it means that this arrow is going to be large in x, going to the right, but it's going to be tiny, a little bit just tiny, going down, because we have 1 over mu. So we will have something like this. So actually you can follow the trajectory of that arrow and see that nothing changes much. After arriving to the null line, so in the null line you are obliged to go only in the vertical direction. So you have like a strong turn. So you have a turn towards the down part. And what happens now? So this particle, if we're following the trajectories like a particle moving, we see that this particle is not allowed to go to the right anymore. It has to go to the left, because now we are below the null line. Okay, therefore x has to be to the left, so the change in x has to be to the left. But in this case we see that the particle has to move to the left, but has this somehow obstacle. So this is like a wall. It cannot cross, because you cannot cross this in a different way than just a vertical line. Okay, so the only way is that actually it closes and it goes actually to the left, and it follows this trajectory all along. Since this is gonna be very small, so the change in x actually is gonna be small, even though mu is large. Okay, and this is actually be also small. So basically, after a very fast trajectory in here, because the rate of change in x was big, we are in a region when the every change in x and y both are very small. So we have to just be patient, and in this moment the particle gets somehow liberated, because there is no any more obstacle at the left. So the particle can start growing, so changing to the left. So this distance is gonna be larger and larger, and then you will have a very fast evolution until you arrive to this wall, and the same process repeats. So you just have moving upwards, and they just follow in a very slow motion this trajectory until you get liberated again, and then you go to this point. So let me just draw these lines. So we go very slowly, very close to this trajectory, then go very fast, then again we cross in a vertical direction, and then we go very slow, and then we go again very fast. So if you draw this in time, so this is going to be t, and this is going to be the corresponding amplitude x. Then we will have, let me just draw it with with blue, something like this. This is actually also shown in the book. So there is a part in the signal that just goes very, I mean, you just see there is no change in x, almost nothing, but time evolves. So it means that this change is very slow. And then there is a big jump, which is actually as a large change in x in a very reduced amount of time. So this is going to be the fast evolution, and then repeats. So slow, fast, slow, fast. So this is like almost like a square signal. And you can think about other kind of signals. For example, a very classical one as well is the sawtooth, which is something like you go slow, fast, slow, fast. Just to point out, this is not this, okay? This is the one that corresponds to this. This is just another example of a low fast signal. And these kind of situations are found very commonly, very common in nature. For example, in our department, we work with combustion instabilities. I already said to you that before. And then we have the situation in which this is, imagine you have a burner, these are walls, and here we have a flow coming in, and then you have actually here a flame, like a Bunsen type flame. It's nice to see that when you introduce an oscillation, you will have maybe as a small evolution. So imagine you have a perturbation at the base of the flame that propagates along the flame sheet in a very small way, but after a certain time the flame is gonna look maybe like this. So another time it's gonna look very long, so it's elongated. So this increase in heat release is actually somehow given by this evolution of this quantity. In this case, x is gonna be heat release. But then at some moment the whole thing just burns, so it's a strong change in the flame surface, and then you get a very super tiny flame. So something like it goes to the original shape more or less in a very fast way. So you just have a very slow growth of the flame surface, and then a very drastic change to the original, or to a position close to the original shape of the flame. So this is given by this. So this is just to show you that this kind of situation may happen in a large amount of problems in nature and in engineering. Okay, so now to finish this exercise, let's compute the period of this oscillation. So this was this signal I just showed you that resembles a square signal. So the idea is to just define that we have like certain like points in the cycle that are important. So there are a moment when we go from A to B, then from B to C, to C to D, and then from D to A. And if we want to know the period of the whole oscillation, we can actually say that this is very approximated in a very good way to 2 times the period from A to B, because this is basically the same as this. So when we go again from A to B, from C to D, it's gonna be the same. And the time that it takes from D to A and from B to C is super small, because it's a very fast evolution. Therefore, the whole period can be actually characterized by this simple relation. Additionally, to facilitate the analysis, we will replace the original problem, because the original problem, you see that we have the evolution in the trajectory is very close. So the blue line is very close to the white line, but it's not actually the same. To compute this, we will actually say the evolution, so the trajectory blue is actually the same as the trajectory in white. So they are actually superposed. So this new problem, that is an approximation again of the original problem, is going to be given by this. Is going to be given by y is equal to f of x, and y dot is equal to minus mu x. So this is the problem. So this is not the same problem as this one, okay? But then we will just try to compute the evolution in x from A to B based on this problem. Now we need to have the x dt. So we can use the chain rule in here to do that. So we can have dy dt is equal to dy dx dt. Voila, we have dx dt as we wanted. And we know already that dy dt is minus u1 over mu x. And we know that dy dx is just the derivative of this function, which is gonna be, let's just write it down, x squared minus 1, and this is multiplied by x dot. Well, actually here is better to have the original notation dx dt, because we need to integrate with respect to t. So we have dx dt, and now we just rearrange the whole thing. We have dt is equal to minus mu x squared minus 1 over x dx, and then we just integrate from a to b, like dt ab equal minus mu ab so now we can write, so tab is equal, and then we can just split the integral, minus mu a b x dx minus a b 1 over x dx. Then we have ta b is equal to minus mu x squared over 2 from a to b minus natural logarithm of x from a to b. Here's just some brackets. So you can yourself prove the following, but it's possible to compute that this point in here is 1 and this one in here is 2. So things become TAB is equal, okay, we'll just write it. Okay, I just developed the whole derivation, so you can just check, nothing strange. Just to tell you that, so we have computed the period from A to B to be here, this, and therefore the whole period is going to be approximated by 2 times this. Okay, so this is the end of this exercise and of this first part of the limit cycle session. We will continue next week with the second part of limit cycles, when we will talk about perturbation theory when considering 1 and 2 time scales. This is actually very interesting to be able to understand and have some analytical derivations of weakly nonlinear equations. Okay, so bye bye.